Hello. So in this new video, we'll talk about the Slutsky equation and Roy's identity, and also make a brief summary of the relationships between the UMP and EMP. Okay. So before we formally introduce the Slutsky equation, so let's have a quick review on the related substitution effect and income effect and the total effect. Okay. Good. So talking about the substitution effect, so this is a problem when we are changing some price. Let's say, okay, so here we are changing the price of P1 and decrease that to P1 prime. Okay, so here we can substitute X2 for more X1 because X1 is now relatively cheaper. Okay, so then here we can use the Hickson demand to represent this substitution effect. Okay, so we might wonder that why we are using this Hickson demand. Okay, so this is simply because in the Hickson demand here, we will have this fixed level of the utility requirement that we're going to apply or going to achieve under this cost minimization problem or the expenditure minimization problem, right? So after we change this P from P1 to P1 prime, then the extra demand that we can obtain for the X1 will be this difference between those two demands, okay? And that is indicated from this distance on this figure as we change this. First, we change the slope as we change the price. And if we want to hold the same level of the utilities, which is U lower bar here in this case, then we have to change this amount of X1 from A to C, and that will be this difference. Okay, good. So in other words, Hickson demand will be a very nice, exactly the representation that we're going to use here to indicate this difference, right? Because that satisfies the requirement that we want to fix this utility level in this case, okay? Which is on this green, on this blue indifference curve. Okay, so that was about substitution effect, and if you also remember the income effect, so that'll be the effect or the change still from the price of X1, let's say from P1 to P1 prime, and that'll be the difference between the total effect and the substitution effect we just talked about. Okay, so the total effect will be just the difference of the change of the order sentiment. Okay, so those axes, and the substitution effect will be the changes of the Hickson demand, which is the H's. Okay, so in other words, the income effect that we're going to get will be the difference between those two differences. Okay, so the first part here will be this difference between the order demands, and the second part, the second difference will be the difference between the Hickson demands. Okay, so intuitively from this figure, we can see that from point A to point C, that is the substitution effect we just talked about, right, in the previous figure. So here we fix the same level of the utility, which is the U lower bar, okay, to get this Hickson, the difference of the Hickson demands. And we want to see here how do the X1 and X2, they substitute each other as we change the price from P1 to P1 prime. So that was the substitution effect, okay? So how about the income effect here? So the income effect will be the change from this point C to point B. Okay, so that's the basic idea is that we know that after all, this P1, it decreases, right? So why not speak previously when we were looking at the substitution effect, we were holding the same utility level as this U lower bar, right? So now we're thinking that, okay, well, since P1 decreases, so why not we can buy even more of both goods, right? So that we can increase utility at this new price. Okay, so when we shift this green dashed line, this new price to some price, let's say here, they have the same slopes, and that is tangent to that this upper blue curve, this indifference curve, which is higher than the previous one, right? So at this new price P1 with this same slope here, and even with this consumption bound of B, we can even buy more of both two goods. Okay, so this difference from C to B, and that'll be this income effect. Okay, so and in other words, that'll be the total change from A to B and minus the change from A to C, which was the substitution effect. Okay, so that'll be the income effect from C to B. Okay, good. So those are just somehow a somewhat straightforward or intuitive analysis, right? So how do we formalize those analysis? So that comes to this Slutsky equation that we're going to introduce. Okay. All right. So that'll be the proposition in 3.G.3. So now we have the same very common assumption that we did as before, and we suppose that there's a continuous utility function, which has local non-satiation and defined on some strictly convex prevalence relation on this set of alternatives, which is L-dimensional possible real numbers. Okay, so this is just the same assumption as before. We want to make sure that we have those Hickson demand function and Wilson demand function instead of correspondence. Okay, so for all the pair P and W, okay, and the utility to be this indirect utility V, given P and W pair, so the Slutsky equation says that we have this equation as below, so which is just the relationship that we mentioned before regarding the three effects. So it's saying that the substitution effect on the left-hand side will be the partial derivative of the Hickson demand with respect to the change of pK, and that'll be the total effect, and which is this partial derivative of the worst demand with respect to the change of pK, and the income effect of this, where we have this partial derivative of the Orson demand, but this would be the derivative with respect to this W, and multiplied by this xk. Okay, so and you can move those terms around and make the positive sign to the negative, and you can make any combinations of those and make some interpretations. Okay, so now let's get to the proof of the Slutsky equation. So we said that given some P bar and W bar pair and some fixed level utility level U bar, so we notice that this we have some fixed level of the budget, some wealth W bar, which is the expenditure of this P bar and U bar. Okay, and we also have this from before, and which is just the relationship between the in UMP and EMP, and we have those two to be the same, which is the Hickson demand after, which is the exactly the Wilson demand if we take this expenditure to be this W. Okay, so then we can differentiate this. Okay, and on the both two sides, and with respect to the pK. Okay, and then we evaluate this total differentiation at some point, which is P bar and U bar. Okay, and that would be, keep in mind that this is just one entry or one dimension in this vector, right? But that'll be true for all the dimensions. Okay, after we take the derivatives, and that gives us this. Okay, and so left hand side will be the partial derivative, and right hand side we just use the chain rule here, right, for this part, and those together will be this this partial derivative. Okay, good. So now the next step is we want to have this to be xk, right? So that'll be something that we need to show next. So we're gonna use another. So essentially, we want to prove this, right? So this is proved in the textbook on the proposition 3.G.1. Okay, so that's saying in this proposition, it's talking about that. So this Hickson demand, this H, will be just the gradient of the expenditure taking P and U and with respect to this P. Okay, and the gradient will be just the derivatives with respect to each dimension, and that'll be just the derivative for a vector. Okay, so here, or that is, we have this H to be the partial derivative of this E, and with respect to this PL for all the L. Okay, so those are the same thing. Okay, so how do we prove this? So we just take this gradient for this expenditure E. Okay, since we have this E to be P times P in the product H. Okay, and after we take this gradient in the each dimension of those, and this is what we get. So from the Kuhn-Tucker conditions, when we're solving the EMP, the expansion minimization problem, so we have some complementary slackness as we did that in the UMP, right? So this will also have that. So here we have something as this. So this price can be represented by some constant. So that here will be just some multiplier lambda, right, in the Kuhn-Tucker conditions. And that is multiplied by this gradient of U. So then we can plug this P into this above, okay? So, and then we can get this. So because we know that this utility will be just some constant, some U, okay? So this thing inside, okay, so this has to be 0 at the same time. And then this gives us the final result of this that we are going to prove, okay? And then we simply plug in this into this Slutsky equation that we're going to get. So this part becomes H, okay? Good. So then the else will be very relatively simple. We know that W bar will be the expenditure of P bar and U bar. And then this term here, we can simply use the X to represent that, okay? And finally, this simplifies to the final Slutsky equation that we normally see, okay? So which is talking about the three effects. Okay, so besides the three effects represented by the Slutsky equation, so another or an alternative interpretation of the Slutsky equation is to use those following two graphs. One is for a normal good, another one is on the right hand side was for the inferior good. For those, to use those graphs, which are representing the relationships between the price and the demand. So to try to interpret this Slutsky equation. Okay, so let's have a look on the left hand side first. So essentially, this kind of interpretation here, it addresses the difference between the slopes. Here it would be, remember that we in the Slutsky equation, those are essentially just some slopes. Okay, so which is the X function regarding with respect to the P, and H function with respect to the P. Okay, so here would be, we have the same thing here, right? So on the left, if we have, okay, so be careful that those dimensions are the P and X. Okay, those are not two X's. Okay, so here it simply describes the difference between the slopes. Okay, so this will be, if we want this curve to be the horizontal demand X, and this one to be the Hickson demand H, and the first figure here essentially describes the difference between those two different slopes, which are the derivative, the partial derivative of X with respect to P, or the H of that. Okay, so since on the left this is a normal good for this X, okay, so if we want to change this P and increase that above some level of PL bar, so here we must increase the wealth if we want to keep to have the same level of utility. Okay, so therefore, because this is normal good, so its demand, it should fall by more in the absence of this composition. Okay, and it will be similar, likewise for the inferior good on the right. Okay, so this is also a very interesting interpretation of Slutsky equation, instead of the traditional, the one or the classical ones that we normally see to represent those three different effects. Okay, good. So the last, or the second last thing that we're going to talk about today will be the Roy's identity. Okay, so this will be the proposition in 3.G.4. So Roy's identity mentions some thing as follows. Okay, so it's saying that the worst demand X given the pair P bar and W bar. So this would be the negative, okay, of 1 over the gradient of this interactivity V, and with respect to the W, and multiplied by the gradient of V with respect to the P. Okay, so it's talking about these relationships, on the relationship between the worst demand and the interactivity itself. Okay, so this is just talking about the UMP itself. Okay, so let's see how we can prove this. Okay, and that would be if we expand all the dimensions. So for all the dimensions L, we have this. So this is the same thing as above. Okay, so how do we prove this? So first, we use the definition for this interactivity, which is the V of this P and E, and that should be, we miss a bracket here. So this would be this U bar. Okay. Okay, so if we differentiate this with respect to the P, and then evaluate the whole thing at P bar, okay, and then this gives us this equation below. Okay, so again, from the proposition 3.G.1, we have shown that the gradient of the expenditure E with respect to P, and that'll be just the Hickson demand. Okay, so here then we can plug this. Okay, and then we can get this as below. And the rest will be very simple. We can just plug in the W bar as this E, and that gives us this equation as in the Roy's identity. Okay, talking about the X, the relationship between the X and the derivative of V itself. Okay, good. So that'll be the Roy's identity, and then we have collected all the pieces that we need to summarize the relationships between the UMP and EMP. Okay, so essentially, the UMP and EMP, as we said, those two, they are dual problems. Okay, so although they have different constraints, they have different object function. One is maximizing the utility, another one is minimizing the expenditure, but essentially they're solving kind of the same problem. Okay, it's just in the different formats. So okay, so the details, so we have 4 main ingredients here. Okay, so the first one will be this worst demand. Okay, and in the UMP, and this value function for the utility will be represented by this V. So for the expenditure minimization problem, we have the corresponding solution, or this set of consumption will be this Hickson demand. Okay, and the corresponding value function will be this E, expenditure function. Okay, so today we talk about the Slutsky equation. That'll be linking those two, right? So that talks about the relationships between, especially it's not the level of themselves, but it's about the gradients or the derivatives of those two, of the X and H, the Hickson demand and the worst demand, right? So that was Slutsky equation, and also talking about the 3 different effects. Okay, so and the last thing that we talked about was the Roy's identity, right? So that links this interactivity V to this Roy's demand X itself. Okay, good. So, and in other words, so now let's have a look on the right hand side. So if we have this So this was the 3 point, if I remember correctly, 3.G.1, right? So we have already also proved this using this gradient of E to represent this Higgs demand. So that was also some result we obtained today. Okay, so what else? On the bottom here, okay, so previously we have already known this, right? This is not difficult to prove if you're interested to show this. So we can always represent this expenditure function using the integral utility or the other way around, okay? So the remaining would be the some other relationships we also discussed previously, is that if we use this, we can use this H, okay, and together with this indirect utility to represent this warrants of demand, or the other way around, we can use the warrants of demand and also this expenditure function to represent the Higgs demand. Okay, so that those together complete this whole figure or this whole map for the relationships between the UMP, the dual problems of UMP and EMP. Okay, and I hope this will be useful. Okay, good.